such that, what was it, number of edges to the power t over n to the 2t minus 1 minus n choose s r over n to the t is at least a for some t. Then there is a subset of the vertices of G with the following properties. Size of A is at least A, and every S subset of A has at least R common neighbors. So, at least R common neighbors. Together, right? Hopefully. Okay. So this sort of strange sounding lemma, in fact, is incredibly useful. So, why is it useful? It's useful, like the regularity lemma is useful for finding subgraphs, particular subgraphs in a graph. You know something, some fairly weak information about the graph, like how many edges it has, and you want to find a particular subgraph H. And we saw the regularity lemma was useful because we had this embedding lemma. So again, given a statement like this, we want a corresponding embedding lemma. There it was using the concept of epsilon regularity. Here we want to use somehow the properties of this set A. What we want is an embedding lemma. Okay, so what's the embedding lemma going to say? So so G is a graph. Okay, so I guess I should say, sorry, for every G and H be graphs. Okay, so we're going to try and find a copy of H inside G. If there exists a subset of vertices in G such that I'm sorry, I'm going to need one more condition. So dependent random choice doesn't let you find any old graph, but it will let you find bipartite graphs. So we can do this for H bipartite, such that, say, A is at least as big as the number of vertices of H. Maybe it only needs to be as big as in one of the sides. And every subset of A with so maybe I'll need some notation. I think I will. So let H have vertex sets X union Y. Let's let delta X of H be the maximum degree of V over V in X. Okay? So it's not quite the maximum degree in the graph H, it's the maximum degree from the left. Okay? You just go out one side. suppose for every S set in A of this size, the maximum x degree in H, you have many common neighbours, many being the number of vertices of H. So what's the obvious conclusion? Then H is a subgraph of G. Okay. This is the lemma we're about to prove. I think that's right. We'll see. Okay. So the claim is what? If you have a set A like it you get from the dependent random choice, where it's reasonably big, and every subset of a given size has many common neighbours, then you can find a copy of whichever bipartite graph you want. The proof is very simple. The proof is basically you just embed greedily. You're trying to find a copy of H, and you just look for vertices one by one. So, how do we embed it? We say, okay, so step one, let Y, which is half the vertices of H, be some arbitrary subset of A. Okay. So Y is in our graph H that we're trying to embed, and A is in our graph our graph G. Okay. So we're trying to find a function phi that maps vertices of H into vertices of G. It's injective, such that if you do this injection, you actually find a copy of H, right? Such that phi of U, phi of V is an edge of G whenever UV is an edge of H. This is what we want. Is that okay? So I'm not quite sure I'm not sure how formal to be with this proof. I always feel that if you're too formal, then you get lost in the technicalities. But I'm always a little worried with this proof that if I just wave my hands, then no one will understand what's going on. So this is sort of formally what's going on, but this is informally what's going on. Right? So this is not a precise statement. This is sort of some nonsense, but it's what you should think. Right? You should think that I'm picking a subset of A, and that's Y. That's half the vertices of H. Okay? But if you're worried about being rigorous, then you should be thinking in these terms. So anyway, I'll perhaps go on being a little hand-wavy, and you can complain if it doesn't make sense. I hope. Okay, so we have our set of vertices A in G, which has this nice property, and we pick a subset of them, we make that Y. And now we want to pick X. So what do we do? Well, what we do is we look at a vertice. So for each vertex of X, let's call it an X, make it even clearer, you in turn maybe. So I'll go through them one by one. consider the neighborhood in H of X. Okay? Which is a subset of Y. So we have some vertex X of H, and it has a neighborhood in Y. Neighborhood of X. Okay. And we'd like to find a vertex in G that has this neighborhood. Or at least this is a subset of its neighborhood. So what do? Well, we look at this neighborhood, which is now a subset of A. How big is it? The size of this thing is at most the maximum degree of a vertex in X, right? Just by definition. Okay. So therefore, this set of inside A has size at most this, and by assumption, we know the set has at least number of vertices of H common neighbors in the graph G. So this thing is going to be our S. This is the common neighborhood of S. Okay. And we want to find this X. We're going to put it in the graph G. So we just pick one of these elements. Okay. And this element now has the correct neighbors. Okay. Maybe it has more neighbors as well, but that's fine. Right? We just want a subgraph. So now you should be thinking, well, you just needed one vertex and you got V of H of them. But why is that necessary? Because we might have used some of these vertices already. Some of them might be inside Y, or some of them might have been chosen as earlier X's. But because we have one for each vertex of H, and because we haven't finished, we only used this number minus 1 so far, there's always at least one left over that we can choose. Okay. So. Okay, so a lot of blank faces, so let me say the whole thing again. So we have a set A in our graph G that has a nice property that all decent-sized subsets have many common neighbors. We want to find a copy of H in G. And H has vertex set X and Y. So we put Y inside A arbitrarily. And then, in order to choose the vertices of X, we just look at them one by one, in whichever order, and we say, okay, I need this vertex to have a certain neighborhood in Y. So I have to pick one of the common neighbors of that set of vertices in G, in the graph G. But by assumption, that set of common neighbors is big enough so that I can always choose one no matter what I've done before. No matter how I've embedded the previous vertices, there's always one left that I can use. Some nodding. Please complain if you don't understand. I think that there's no harm in spending another 5 minutes on this, but you should complain. So I think some people are now happy-ish. Tell me which part is the problem, or all of it. No? Everyone is very quiet. You all lost your voices in Carnival. So, I'll say just the same thing one more time. I don't know a different way to explain it. There you have a set A, which is big and has a nice property, and we want to embed H. So H looks like, this is H, it's got a Y and an X, and then some edges. So we just take Y, put it in A, and then for each vertex of X, we look at the neighbors we wanted to have, we look at the corresponding neighbors in G, the corresponding vertices in G, look at their common neighborhood, it's big, so there's a vertex that we can use. Okay, good. So very simple. Right. Now, using these two lemmas, we're going to prove some nice theorems. So, first application. Now, we already saw an application last time very quickly. Maybe I'll do a couple of others and maybe see the other one again. So, first application. The Ramsey number of the hypercube. So what does this mean? So we've seen Ramsey numbers Rk and Rst. The Ramsey number of a graph is a very closely related concept. So if G is a graph, then we define the Ramsey number of G to be the minimum n, such that if you have a coloring of the edges of the complete graph on n vertices with two colors, then there exists a monochromatic copy of G. So you take the complete graph on n vertices, color the edges red and blue. If you have to find either a red copy of G or a blue copy of G, then you'll release the Ramsey number. So in particular, R of k, which is the Ramsey number we're familiar with, is just the Ramsey number of the complete graph. Okay. Next, what's Qn? This is the hypercube. So Qn, here is Q2. It's a 4 cycle. Here's Q3. Also, probably quite familiar. Okay. So in general, Q. I'm going to call it QR, sorry, because N is going to be something else. QR has vertex set 0, 1 to the R, and edge set points at distance 1. Okay. So UV is an edge of QR if U and V differ in one coordinate. In exactly one coordinate. Okay. So that's the case here. This is 0, 0, 0, 1, 1, 0, and 1, 1. So this is a vertices of QR is 2 to the R, it's R regular, and it's bipartite. So, this one is clear, right? Why is it R regular? Well, each coordinate you can change. So you have one neighbor in each coordinate. Why is it bipartite? Well, things with an odd number of ones and things with an even number of ones can be neighbors, but odd and odd cannot. Okay, good. So famous conjecture of Burr and Erdős from the 70s, I think, says that the Ramsey number of QR is a constant times 2 to the r. Okay. So it's certainly as big as 2 to the r, because if it's smaller than 2 to the r, there's no copies at all. They conjecture that it's within a constant factor. This is surprisingly difficult. So Beck managed to prove that it was at most 2 to the constant times r squared. Beck's a pretty famous guy, particularly in games, combinatorial games. Graham, Erdös, and Rachinsky managed to prove that it's at most something like a constant times r to the r. This was quite a big improvement. These are also all pretty famous guys. And then finally, Kostochka and Erdös. I think I got this right. I'll cheat in a second. Showed us at most 2 to the constant times r, where the constant is about 2.6. Okay. So the result is pretty good, it's pretty strong. The proofs are pretty complicated, and the guys are pretty famous. So we're going to prove the following bound. In just a few lines. So I'm not sure who to credit this to. I think probably Fox and Sudakov. Right? The Ramsey number of QR is at most 2 to the 3r. Okay, so this is slightly worse than this bound, but the proof is going to be almost immediate. And if you work a bit harder, as they did, then I think they got down to 2 to the 2r or something. So really this method gives the best known bound. Not quite the proof I'm going to tell you, but not much more complicated. Okay. So what do we want to prove? Now let n be 2 to the 3r, and let C be a two coloring of the edges of 0, 1. What we want to prove is that there exists a monochromatic copy of QR in this coloring. And the first step is completely ridiculous. So without loss of generality, C to the minus 1. So there are more red edges than blue edges. Okay, at least as many red edges as blue edges. Let G be the graph, be the red graph. Okay. And we're going to find a copy of QR inside G. So we're not, even though we're proving the best possible, the best known bound on the Ramsey number, we're actually doing something much stronger. We're going to just do the extremal version. We're going to say that with this many, if n is this big, and you have half of the edges, already you find a complete a hypergraph on an R-dimensional hypergraph. Okay. So the number of edges of G is at least n squared over 4. So the claim is that there's a copy of QR in G. Okay. So, how do we prove it? Using our two lemmas. So what do we want? So by the embedding lemma, if there exists a set A in the vertices of G such that size of A is at least 2 to the R. Actually, we only need 2 to the R minus 1, but let's not worry if you think about the proof. And every, how big set? Every set of size, this is the degree of a vertex in the graph, that's R, we noticed before. Every R set, so I realize my R is the wrong one, but never mind, has how many common neighbors? We need 2 to the R, then done. The embedding lemma says that if we can find such a set A, then QR must be a subset of G, a subgraph of G. So, let's find such an A. Obviously, using the dependent random choice lemma. So, by dependent random choice lemma, with what do we want? So, A equals 2 to the R. S equals R, and R equals, sorry, that's absolutely terrible choice of letters. 2 to the R. Different R. So we're done if what? We're done if number of edges of G to the power T over n to the 2t minus 1 minus n choose R 2 to the R over n to the power T is at least 2 to the R. Right. So we just want to find the value of T such that this holds. Right. What is the number of edges of G where it's at least n squared over 4? So this would be implied by let's see. So n over 4 to the t, right? Minus, this is at most, en over r to the r times 2 to the r over n to the power t is at least 2 to the r. What would you like to take t equal to? And what's n? N is 2 to the 3r. 2 to the 3r, 2 to the 3r, 2 to the 3r. Is 2 to the minus 2rt. And this thing is basically 2 to the 3r squared.
The r in...
Sorry? This is the r as in the size of the cube.
And the r is 2 to the r?
2 to the r is the number of vertices of the hypercube. So it's the one that we're using in the lemma for our common neighborhood. Yeah. So we're on a 2 to the r here.
Yeah.
And we want all the sets of size S. We want the sets of size R. Yeah. Okay. So what do we want to take it to be? This is like 2 to the 3r squared, 2 to the minus 2rt. So we want this to be, we want this term to be small, basically. But without making this term small. So let's take t equal what? 2r will do, right? Maybe 2r minus a little bit. Then the left-hand side is equal to 2 to the r plus 1 minus something really, really tiny. Basically, something less than 1. Right? This is 2 to the 4r squared. This is like 2 to the 3r squared. Okay. So these proofs are really very easy. Once you have the dependent random choice lemma and the embedding lemma, you just back out exactly what you need. There's no need to... So this proof can seem sort of magic if you start out by saying, apply it with some random numbers, this gives you a set which magically works. But everything is sort of completely obvious. And you can see at the end there was some slack, right? That I didn't choose everything optimally. And with some more work, then a couple of little ideas, you can get this down to the best known. So there was sort of nothing happened. You want to find a particular graph. Well, you have it by the embedding lemma if you have a set A with certain properties, and that immediately leads to a condition on the number of edges of the graph. Yep.
Isn't T too big? I think the first number is smaller than...
Thank you. I did this badly. I wasn't very careful. So maybe I was even less careful than I should have been. Okay, so I'll tell you where I lost a factor of 2. Because I thought when I first wrote this it didn't matter. But there's actually a 2 here, which I took out to make the statement prettier. Yeah. So, anyway, apologies for that. If you remember from several weeks ago when we last saw each other, so this comes from the fact that this is the sum of the degrees, right, which is twice the number of edges. So, thank you. So, in fact, you get a 2 to the t. So here there's only a 2 to the t. Good. Okay, so I have time to give you another very easy application. Which works in basically exactly the same way. So, extremal numbers of bipartite graphs. You'll recall, well, so I hope everyone still recalls what this number is. Let me just write it down anyway. Maximum of edges in a graph on n vertices with no copy of h. And recall also the extremal number of nkst is almost a constant, and the 2 minus 1 over s for all s and t. Okay. So the complete bipartite graph, so all bipartite graphs have extremal numbers little o n squared, and in fact they all have a most n to the 2 minus epsilon. Okay. So let's prove the following big generalization of this fact, which I think is due to Alon, Krivalevich, and Sudakov, but I could be wrong again, which says the following, that so let H be bipartite with say on X union Y with maximum degree on one of the sides of most S. Okay. So that was the situation in KST. Every vertex in the T set has degree S. Then we get the same result. So it basically says that once you know the degree on from one side, the maximum degree from one side, it doesn't help you to take a really big bipartite graph. Or it doesn't help much. It doesn't help to take a very sparse one. You might as well jam everything together in KST. It's as bad as it gets. Okay. So, I think I've babied you too much. So now you can tell me how to prove this. So, number one, embedding lemma. Means you need to set A with what? What properties of A do you want? Uh-huh. all S sets have at least how many V of H common neighbors? Right. Cool. So if we can find such a set, then we're done.
The cardinality of the S is S.
Right. So we want this to hold for every subset of A with, degree of S neighbors. Degree is S. So sorry, I'm writing S sets for sets of size S. Yeah. Okay, so by dependent random choice. So we're going to apply it with A equal number of vertices of H, S equals S, and R equals number of vertices of H. What we need is the number of edges of G to the T over n to the 2t minus 1 minus n choose S, number of vertices of H over n to the T is at least number of vertices of H.
You don't make 2 to the T?
I don't think it's going to matter this time. If we need it later, I'll put it back. So what do we let T? Would you like to set T equal to? So the number of edges of G is going to be equal to some large constant times n to the 2 minus 1 over S. Right? So we're going to get n to the 2t minus t over S over 2t minus 1. So what do you suggest for t? We're also going to get over here an n to the S over an n to the t. We like this term to be small, as usual. Any suggestions? S plus 1 will make sure that this one is small. We'll get 2t minus S plus 1 over S plus 1. So both terms will be small. So not quite. Take t equals S. And we get c to the S, n to the 2s minus 1 over n to the 2s minus 1 minus en over s to the s times some small constant number of vertices of H over n to the s. This equals c to the s times what minus the n's cancel. You get basically E V of H over S to the S. And I claim this is bigger than V of H if C is large. Right? Because this thing is just a constant and this thing is big. So it's almost like magic. There's all kinds of things that you can do just by applying these two very simple statements. Remember, we proved this just by considering the expected value of a couple of variables, subtracting, and we proved this just by the greedy algorithm. And yet they give these quite incredibly powerful results. I find it still quite shocking. Okay, so let's take a break. And then afterwards I'll tell you a little bit about additive number theory, additive combinatorics, and maybe try to prove the Szemerédi-Gowers theorem. We'll see. And am I right we have one more class on Monday after this? One more class on Monday. Okay.